And I've got a short introduction prepared. So, hello everyone. Today we are thrilled to have Dr. Matthew Delaney and Eliezer Shahid jointly present their workshop End-to-End Photonic Integrated Circuit Chip Design with Luceda Photonics Design Platform. Dr. Delaney is a senior application engineer from Luceda Photonics. He holds a PhD in integrated photonics from Southampton University, where he studied phase change materials for photonic switching. Eliezer Shahid is a photonics layout engineer from Spark Photonics. He holds a bachelor's degree in electrical engineering from the University of Delaware and has previously worked in thin film lithium niobate and graphene material systems. Without further ado, please join me in welcoming our guests.
Oh, cool. Thank you for the introduction. Yeah, before I proceed, I just wanted to, I guess, give a quick overview about Spark Photonics and Luceda. So let me go ahead and actually share a presentation. Um, and where's the share? Oh, there it is. Hey, Chloe, could you turn on sharing, please? I
Yes,
sent a
sorry.
request.
1 second. Sorry, I thought I fixed that in the general settings, but I guess I have not.
No worries. Cool. Thank you. All right, so I'm sharing right now a PowerPoint screen. Should say Luceda Photonics getting started with PIC design. If you can't see the screen, just let me know, but I'll go ahead and kind of do a very quick presentation and then we'll go over some code. Specifically, we're going to be talking about circuit design with IPKs, P-cell design with IPKs, and then we'll go over the lumerical link and Canvas as well. Um, so before I begin, just a quick introduction on Spark Photonics. Spark Photonics is a integrated photonics design company and also software company. We're based out of the Boston area, and yeah, we do all sorts of design projects, and we also are working on tools to help facilitate design. So one tool that we've released recently is Checkmate for DRC. Um, and yeah, um, now I'll go ahead and just give a quick intro on Luceda as well. So before that, here's kind of our schedule for today. We'll do introduction, the online kind of session, and then Q&A at the end. So an introduction to Luceda. Luceda Photonics was born in 2014 from the Belgian photonics ecosystem. And the vision of the company is to help photonic IC designers enjoy the same first-time right experience as electronic IC designers. Um, and so the mission is to accelerate the PIC design team's time to market by helping them to set up a flexible and efficient PIC design flow. Luceda has a global presence on all continents. The head office is in Belgium. Spark is actually the official partner for Luceda for North American software distribution and sales and support. There's an office in Shanghai as well. And then Luceda has two official resellers, one in Taiwan and one in Japan. Um, Luceda has thousands of users globally, and both Luceda and Sparks are teams of photonics experts. So now that we've got the introduction done, I just want to talk very quickly about the Luceda design platform, and then after that, we'll jump into some code. So, um, the uh, Luceda design platform is kind of centered around a code-driven flow. So essentially, what it is that it's Python powered. So everything that you want to do in your photonic design flow is done with a single language with Python. So component design is done in Python, circuit design is done in Python, design validation is done in Python, along with simulation, circuit level simulation, and even linking to device level simulation software is all done in Python. And so the first time, right, photonic IC design software, kind of the experience of that. Essentially, like what that means is, it's meant to reduce design errors, and it's meant to help you design manufacturable PICs right out of the box. Luceda has over 30 PDKs on many different material systems. Luceda also offers assembly design kits or ADKs, which are basically PDKs, but for packaging houses. And Luceda also offers a TDK, which is a testing design kit. And that's essentially the same as a PDK, or same as a ADK, but it's for setting up your chip for a testing house. Um, the first time right experience also includes leveraging a standard language. This means Python in our case. And, what this means is that you're not going from Python to lumerical script or, anything different. You do everything in Python in Luceda, and you're able to do all parts of your photonic design flow through Python. And then all of this kind of works together to improve the time to market because you're able to not only, you know, not only are you able to use the power of Python to, quickly make your structures and your circuits, but now you have code that's reusable. So you can write the code such that it's reusable and reconfigurable. So if you have a similar project down the line, or if you have a project that includes something from a previous project, you're able to kind of recycle that code and save yourself a lot of time from remaking things and redoing things. So the design platform is centered around Luceda IPKIS. Luceda IPKIS is essentially the platform where you do all of your component design and your circuit design. Parts of the Along with the with Luceda IPKIS, we have our kind of flagship products, which include AWG Designer, which is a tool to help you design AWGs, and Luceda IP Manager, which helps to manage your IP. We also have links to many different third-party software such as Lumerical, 3ds Simula, Tidy 3D, Siemens EDA, and then Checkmate DRC, which is from Spark Photonics. Um, one note about the AWG Designer I want to make is this tool is actually very, very powerful and very helpful. Uh, about 2 summers ago, Spark had an intern, and his summer project was to design an AWG. And using Luceda's AWG designer, he was able to do that in about 2 weeks. So it's super powerful in that sense that, very, it can really streamline the process for it. Um, we then have the Luceda design kits. So these are all the PDKs and then the assembly and testing. So we have many different material systems: silicon, silicon nitride, indium phosphide, um, aluminum oxide, lithium niobate on insulator. We're partnered with many different foundries. If there's a foundry here that you don't see, let us know. Chances are we're already either working on the PDK for it, or we're in discussion with getting their PDK on our platform. But yeah, just reach out to us, and we'll definitely look into bringing that PDK onto the platform. Um, yeah, so Luceda IPKIS has a many different kind of features and kind of facilitate helps you to facilitate different stages of the design process. So first thing we'll talk about is component design. So again, we're using a standard language Python, and the way that we're able to do component design with Python code is that it's parametric. So the components and the layout and the simulation are all able to be parametric. There's a virtual fabrication feature where you're able to kind of you're able to see what the device would look like when it's fabricated using the PDK. There's a built-in physical EME simulator So you're able to run EME simulations with IPKIS, and then of course, as I mentioned earlier, you're able to do simulations with third-party tools, um, such as lumerical, Teddy 3D, so on and so forth. So circuit design is also parametric, and it is a code-driven circuit design. And we have a bunch of different kind of features and tools built in to make circuit design easy for you. So of course there's optical and electrical routing, there's obstacle avoidance, and then there's a automatic electrical via insertion. There's many different ways that you can route, and I'll show you that in our code demo later on. Circuit design also includes parametric circuits, and this just having both the simulation and the layout in code helps to maintain a tight link. So if you look at this graphic over here, we have a 4-level splitter tree, um, and then we have a 5-level splitter tree on the bottom. And on the right side of our graphic, we have the transmission and reflection data for our splitter tree. Um, Using when you program, your circuit or your P cell or whatever in IPKIS, parametrically, when you do it parametrically, you can really just reuse that same code to then generate a new splitter tree, and the simulation scales accordingly as well, right? So you're not having to rewrite the circuit simulation. The circuit simulation is linked to your layout, and it scales accordingly with your circuit. Circuit simulations are done with Caffe, which is the simulation engine within IPKIS, and uh, we also offer time-dependent simulations and frequency and time domain simulations, and you can even plot eye diagrams. Another part of circuit design is IPKIS Canvas, and so this is essentially schematic capture with code assistance. So what this means is that you have a schematic interface where let's say you wanted to put together a very simple splitter tree. You drag and drop your components in here, you make your connections, and then you can generate code from this to put into your IPKIS code environment. And then you're able to then clean that up, make that code better, and really kind of like kickstart your project. IPKIS Canvas is a good way to kickstart your project. It's also a good way to communicate ideas around the design process. It personally in the past I've communicated ideas with PowerPoint or like drawings on a napkin. And sometimes you can get your ideas across. Sometimes it can get a little lost, but with Canvas, you can very clearly see, okay, this is how everything is connected. This is, what we are intending to do. And then once you have your schematic finalized, you can generate code and get to work on cleaning it up. Validation in IPKIS can be done through Canvas as well. So Canvas uses netlist extraction. So this gives you an accurate representation of whether components are connected or not. So if there's a missing connection in your code, it's going to be reflected in your schematic in Canvas. And if there's something that's misconnected, that's also going to be reflected. This works for both optical and electrical connectivity. And you're able to also inspect properties such as waveguide length. So let's say you had um, like two waveguides that need to be the same length for like phase sensitive applications. Um, you can then select the waveguide, check the length, select the other waveguide, check the length, and ensure that they're both the same length. You can also run post layout simulations using Caffe. This is part of the design validation. So here, we have our circuit here, and we're running a uh, simulation just to kind of verify that the circuit is behaving how we want it to behave. And then there's also 3D export. So you can export your design as a 3D visualization file. And then for tape out preparation, there's a few extra tools that we offer. So one thing we offer is detection of overlapping layers. Um, so if you have two waveguides that cross each other, you can search for overlapping layers and then it'll tell you where they are, and then you can go and you can fix those overlapping layers. Sometimes with a large layout, it can be very difficult to see, especially when you're working with a PDK that has many, many layers, and you're having to look through all the layers in your GDS file. It can be difficult to detect those. So IPCIS offers overlap detection, which tells you uh, where things are overlapping. Layout flattening is also available to fix snapping errors. And then there's also acute angle patching that is available for tape out preparation. And of course, there's a full GDS export. So right from IPCIS code, you can export fully to GDS and have that ready for DRC or tape out or whatever you need. And the Luceda design kits, they all leverage the same standard language Python. And so these design kits, include the component layouts, the component simulation models, and then also just models of the components as well. These also work with IPCIS Canvas for schematic capture and verification. And you can also export to open access and UPDK standards. One thing that I also want to touch upon is that Luceda offers fantastic training and support. And so, what this means is onboarding training, training material and documentation, Luceda Academy, customer support portal, application support, and a bunch of different training events as well. So onboarding training meaning that, once you get a license, you'll either meet with me or somebody else from Luceda, and we'll help you get started with a project in IPCIS, or we're really there to teach you how to use the software. There's also plenty of training material and documentation available online. Luceda Academy is it's like a Python project that comes shipped with every copy of Luceda IPCIS, and that just contains a ton of code examples, which teaches you how to do all sorts of routing and component placement, everything from component placement to routing to setting up a simulation, to setting up a link to uh, lumerical simulation, even like, specific examples if you're looking to work on an OPA or like a PPC or something, those examples are available so you can, kind of take a look at how that's done in IPCIS and, adapt that code for yourself. Um, the customer support portal, you submit a support ticket and somebody will get back to you within 24 hours. Um, and application support and also training events. So application support, if you need help working on a specific feature, we can certainly offer some help with that. And then training events, there's always getting started trainings and then also webinars that Luceda hosts for their users. And so this is just a kind of like an overview of our ecosystem partners. And so, we work with a lot of different, organizations to provide the best possible PIC design experience. And Luceda is hiring, so if you're looking for uh, for a job, feel free to send your CV to HR at Luceda Photonics or check out their career page with the QR code here. Um, and you can also connect with either Pierre, Joris, or Chiara on LinkedIn. All right. And before I continue, any questions from anybody? All right. If no questions, then I'll go ahead and share my code screen and just kind of go over what designing a simple splitter tree looks like in IPKIS. So I've just shared my code screen. Let me know if you can, let me know if you can't see it. And yeah, but otherwise, I'll get started with kind of explaining this code. Um, so what this will do is let me just run this really quickly and kind of show you um, what it does. So what we're going to make is we're going to make a very simple splitter tree with three MMIs and just having them all kind of connected together like that. That's what we're going to make today. So this the code is uh you know fairly short. You import your PDK and you import your IPKIS module. Everything inside of IPKIS exists in a class. It helps with hierarchy. And so this makes it so that we can take our splitter tree and we can put it in a hierarchical structure for our layouts and our P cells. So in this case, we're making a class called splitter tree. We're inheriting i3.circuit, and circuit just contains all the code and utilities for generating and simulating a circuit. Then we are defining our instances here. And essentially what this is first we define our MMI. We say that it's a 1550 1x2 MMI from our PDK. And then we specify our instances. And essentially what this is we're telling IPKIS how many of each component we have. And so we're making a unique instance of the MMI, right? So we have MMI 0, and that is calling this MMI. So this instance of the MMI is going to be different from the instance of MMI 1. And same with MMI 2. Then once we specify our MMIs, then we go ahead and we specify our specifications, right? We choose where we want to place all of our components. So here we're placing our first MMI at the origin, and then we're placing the second one at uh, x equals 100 and y at minus 25, and then MMI2 at x at 100 and then y at 25. Then we have our connect bend command. And what this does is it just connects all of our components together. Here we're saying that connect the output 1 port of MMI 0 to the input 1 port of MMI 1. And then we're doing the same thing here, output 2 of MMI 0 to input 1 of MMI 2. And then we're going to go ahead and in our code execution block, we're going to go ahead and we're going to call our splitter tree class. And then we're going to call the layout for that class. Then we're going to visualize that layout, and then we're going to write it to a GDS file. So that's what happens when I run this code, right? This is the visualization of our layout. And let me actually go ahead and uh, open up the GDS file for this guy as well. So splittertree.gds. Here we go. Here's the splitter tree that we just made in IPKIS. And so this is just a very simple example of how to put a circuit together. I can show you then, next I'll show you a much more generalized example of how we can make a splitter tree, right? So this is like a fully parametric splitter tree. So, in our case now we're having variables that we define for our class. Um, we have a splitter variable, number of levels, X and Y spacing, and then we have property restrictions here. This just basically is saying that these variables can only be restricted to certain things. So splitter can only be a P cell, number of levels can only be a positive integer, and then X and Y spacing can only be positive numbers. Then we're defining our splitter here. So by default, the class is going to call a 1 by 2 MMI at 1550. And then we're using a nested for loop to then go ahead and uh, generate all of the splitters that we need for each level of our splitter tree. So, you can very easily also just hard code everything like this, but with using the power of Python, it takes you maybe like a minute or so to write this, and then now you're able to generate all the splitters you need for your splitter tree. And I think even kind of going further with this, it can be difficult to do this in K layout. When you're placing your splitters manually, and then you have to make sure they're at the correct distance and they're spaced correctly, and so on and so forth. With here, using the power of Python, we're using a nested for loop to go ahead and generate all of our splitters and give them unique names. Then for our specifications, where we tell IPKIS where our components are going and how they're connected, we're again using a nested for loop to then automatically calculate our X coordinate and our Y coordinate for the splitter. And then we are placing the splitter at the X and Y coordinate that we calculate. And then we're using again a nested for loop and conditional to then make all of our connections between the input and the output port. So this, again, just automates your connection process between ports. And then we have a default exposed ports function. So what this is doing essentially is, let's say you want to take the splitter tree and you want to export it into a larger layout. Um, you know, and then you want to connect to that splitter tree in that larger layout. This exposes only the ports that you want to be able to have it connect to, right? You don't want to, you don't want to connect to the ports on the internal of the splitter tree. You just want to connect to the input and then the outputs. So this lets you specify the ports that can be connected, the ports that are available to connect to for this circuit. And again, we're using the power of Python. We're using a for loop to then go ahead and automatically expose the ports. And then now here we have again, in our code execution block, we're calling our splitter tree. We're saying that we want a 4-level splitter tree. We're calling the layout. We're going to visualize it. And I can actually go ahead and make can actually go ahead and export this to GDS as well for us to take a look at. So this is the previous layout I was showing you, but now I will run this, and you can see here now we have a 4-level splitter tree automatically connected between all the ports, and then the ports also automatically exposed. So the cool thing about this, right, is you've spent, a day or so writing the splitter tree code. You have it super parametrized, right? Um, Now, it works for your one project, but now you need to reuse it in another project, right? And now let's say you need like, let's say a 7 level splitter tree. You need a really big splitter tree. You can, call this function and you can call this function and you can pass in your parameter, right? You want now a 7 level splitter tree. So when I run this, it'll go ahead and generate the layout for us to look at. And it's definitely pretty crazy, but if we zoom in, we can see uh, all of the splitters that we've generated and all the levels for it. And now let's say, you want to change up the splitter, right? So um, right now, the default splitter that we're using is our 1550 1x2 MMI, but let's say you want to use a Y splitter, right? So we can go ahead and say splitters equal to PDK dot, see here, Y branch. And now we'll do splitters equal to splitter. And this will now generate a 4 level splitter tree using a Y branch. So if we go ahead and we zoom in, we can see that we're now using Y branches to connect, just to do all the splitting for us. So, this is what I mean when I say, you write once, reuse it as many times as you want. In this case here, we wrote the code once, and now we can make a completely different type of splitter using a Y branch as opposed to a 1x2 MMI. We can change the number of levels that we want for our splitter as well. And as I've shown in here, it's all pretty uh, automatic, right? The way that we kind of set this code up for. It's reusable and reconfigurable. Um, and so, especially with like when you have multiple people on a project or you need to reuse resources, having uh, you know, code that you can reuse and reconfigure is saves a lot of time. One thing I also want to show you as well is um, just like some additional things we can do for laying out and connecting our splitter tree. So now we're preparing this for a chip, right? So we call our splitter tree. Now we have grading couplers that we want to use to connect to our splitter tree, and then we have a waveguide crossing that we're going to use as well. Um, we have our number of levels, X and Y spacing, and then the grading spacing. Here we're calling our tree, passing in all of the information for it, calling our default grading coupler, default waveguide crossing. And then for our instances, for single instances, we're just going to go ahead and define them in here. And then for our multiple instances, we're using a for loop to generate all of our output grading couplers. And our specifications here now, earlier I showed you the place command, but there's also the align vertical and align horizontal. So what this does is it's able to let you align components um, on one axis or to another port, or sorry, on one axis to another port. So what this means is, we're aligning our output test, or sorry, we're aligning our input test grading coupler. We're aligning that port using the output as our anchor, and we're aligning it relative to the output 2 of our crossing, and we're aligning it in the vertical axis. And then now we have our Connect Manhattan, which is a different type of connector. Previously, we were using Connect Bend, but Connect Manhattan makes Manhattan connections. Um, So we have all of our connections we want to make in here. We have another Manhattan connection that we're making. The only reason why we're calling this again is because we're using control points to now control our route. So I'll kind of go over what this does when I show you the layout, but then we're placing our components again, and then we're using a for loop to place our grading couplers, and we're using a for loop again to connect all of our output grading couplers to the tree. This time we're using a Manhattan bundle connector. So this is going to make a bundle. We expose our ports, and yeah. So when I run this, it'll go ahead and generate our layout, which we can see this is what it looks like, right? So we have our 4-level splitter tree. We have all of our output grading couplers along the top, and then we're using a Manhattan bundle connector to connect just this guy, all the grading couplers between this guy and this guy. They're all being bundled and routed to our uh, splitters down here. And then we have our waveguide crossing here um, to allow us to have kind of, not overlapping waveguides, but kind of allowing us to split light in these directions. Um, yeah. And when I mentioned earlier, the control point, to control the route, normally when you're making a route, you kind of have to make sure that it doesn't overlap anything. So this line right here is ensuring that our route is not overlapping our splitter tree. So, this route is a connection between the waveguide crossing and then this grading coupler here. And we're just saying that uh, we want the horizontal movement to come down by half of the Y spacing, and then we want it to come down relative to the southern um, the southern bounding of our splitter tree. So what it does is when it does the route, it'll come down here. It'll say, okay, here's the southern bounding. And then we're going to go ahead and move it down by half the Y spacing. And so, again, we're using these are, pretty advanced examples, but this just really shows you um, how powerful IPCs can be, using the power of Python and using different connectors and placement options. You can really make just about anything that you want. And then the last example I want to show you is a chip that I put together using an ADK. So if you're interested in, designing your chip for packaging, it's, whether you're using it now or whether in the future you need to, this is an example of designing a very simple example PIC um, within an assembly design kit. So for this example, we're using the Fix ADK, um, and our circuit's very simple. We have a simple splitter tree here that is then being routed to um, our thermal optic phase shifters. And then those are all being routed to the output grading couplers. And then we have, some test grading couplers here, some test electrical lines here. And then we have all of our electrical routing for our thermal optic phase shifters going to our electrical pads. And here we're using an electrical via as an example to show it going between two different layers. But using the Fix ADK, we're able to then have a kind of blueprint our chip can be laid out such that it's ready for packaging um, with fix. So, that was a pretty comprehensive overview on making layouts in IPKIS. I think one thing that, is definitely important as well is making your components in IPKIS. So making your components or your P cells is very similar to making a circuit. You have a class, you have your parameters. The only exception is that now we're defining we're inheriting the P cell class. So basically what it's saying is that everything in here should be treated as a P cell. So again, we have our properties. We're now defining a default trace template. Trace template is essentially the best way I can describe it is like a cross section of a waveguide. It defines how waveguides are connected. Um, then we have a validation function just to make sure that the properties that we're passing in aren't going to generate a super weird and crazy MMI. Now we're making a layout class for a P cell. We have a generate elements function where we're making all of the elements for our MMI, right? So we have our rectangle, we have our wedges for the inputs and outputs, and then we have another rectangle for the cladding. Here we are also defining the ports. So we have our input port, we define the position and the angle as well as the trace template. And then we define all of our output ports as well. Then here we have the definition for our circuit model. The circuit model essentially just defines the behavior of the MMI. And then, this is when you run a circuit simulation, for, let's say a splitter tree, it'll grab the information from your P cell and it knows how to it knows how the behavior changes when it's become a part of a circuit. Um, so, this is really, again, it's like the circuit, you're putting together a blueprint for how to make your MMI so that once you have a specific MMI kind of like, kind of dialed in and tuned in, you don't have to rewrite it, right? You can instead, either call the MMI, pass in the parameters you want, or you can create a locked property MMI. So in here, we're, making a 1550 optimized MMI. We're inheriting our 1x2 MMI class and everything in here, right? We're not redefining anything. Essentially, we're not remaking the MMI here. We're just defining the default properties for this specific MMI. So we have a specific trace template that we're defining. We have a default width, default length, taper width, taper length. And then we're also telling IPKIS where to get the circuit model data for this specific iteration of the MMI. And so all of this kind of, comes together um, for you know, for you to be able to, make your layouts as efficient as possible, and also get simulation information and also be able to link this to external simulation tools. Um, so I can go ahead and talk about the external. Actually, let me show you guys the very quickly just a circuit simulation of our splitter tree. So, we've made our splitter tree. Now we want to run a very simple circuit simulation on it. So here we're importing our splitter tree, importing NumPy and PyLab, SciFab, and then IPKIS. We call our circuit, call our layout, and then we're going to visualize it. That's what we do in the first step. Then we call the circuit model for our circuit. And then we define the wavelengths that we want to simulate at. And then we're going to run our simulation and pass the wavelengths that we want to simulate at for the circuit. And then this is just a bunch of plotting code here. And so what I'll go ahead and do is run this. And what it'll do is give us a you know, overview of the circuit, telling you, hey, this is the circuit we're simulating today. And then it'll go ahead and show us the transmission of our circuit. And it'll also show us uh, this guy. This is the other transmission. And then reflection of our circuit. And now we have our uh, circuit simulated here. Um, IPCIS also does like time domain simulations. So very quickly, I'll demonstrate that. I know we're running out of time, but I'll demonstrate this very quickly. Here we're defining our ramp function for linear voltage. Um, then we specify our optical source and our voltage drive. And here we're making a very simple kind of circuit to like simple like test bench circuit. We call our MZI here. And then we set up our circuit here. We have our device, optical source, voltage drive, and then the probe. And then we have our link, all the connections we want to make. And then we call the time response for our circuit, and then we plot it. So when I run this, it should go ahead and show us our circuit that we're going to simulate. And then it will also simulation for us. And now we can see um, the response of our uh, MZI, when we're doing thermal tuning in the time domain. So we have our optical output power versus the simulation time. Um, yeah, so there's, these kind of built-in simulation options. But now I want to quickly go over the link to lumerical. So, the link to lumerical essentially, in this function right here is we're making a very simple function where we're going to simulate our splitter with lumerical. So it's going to take a layout, it's going to take project folder data tag, wavelength range, and the simulation gaps. And the nice thing about this link is that when you're writing the simulation, you're not writing numerical code, right? You're basically calling different functions and then passing in the relevant parameters and the relevant information for it. So, in this case, for our simulation geometry, to define our simulation geometry, we're passing our layout, and then we're passing in our bounding box here. Um, and then here we are we're now making our simulation. So we're doing an EME simulation. And we pass in our simulation geometry, which we defined earlier. And then we pass in our monitors. We pass in the output that we want, which is an S matrix over a specified wavelength range. And then we have setup macros. So these are just kind of extra things that you can add to your IPCIS numerical simulation. And in this case, we're defining the group spans, number of cells, transverse mesh, and then we're also setting up our boundary conditions with numerical commands. So essentially, if there's something very, very specific you want to do that within the numerical link that you're either unsure of how to do or unable to do, you can go ahead and pass in these commands. Um, then, we get our result as an S matrix, and what this is going to do is going to print the transmission and reflection. So I'm going to run this guy, and while it's running, I'm going to kind of talk a little bit more about how this all kind of works. So in here, we're not, redefining the simulation geometry, right? We're not going through and we're not saying, hey, this is, where I want, the rectangle. This is the X span for it. This is, where I want the tapers or anything like that. This is all data from your IPCIS P cell. So you write your IPCIS P cell, you pass it into your, numerical link, and then you can simulate right after you finish writing your IPCIS P cell. So essentially, it's like, you write the blueprint for your MMI, and then you say, oh, I want to optimize this at 1550, right? Then you write a simulation routine using the lumerical link, and that then takes your layout information and port information and automatically kind of translates it and puts it into lumerical. The layer information also just automatically goes into lumerical because that comes from the PDK. So if you're trying to optimize a device on a certain PDK or certain process, you don't have to go through and define each layer manually. It pulls everything from the PDK, and then you're able to, uh, you know, really, start from the P cell and immediately jump into simulation without having to remake the simulation or remake the device in the simulation. So right now, this is just, a way for us to inspect. We can see our ports here, and, we can see you got two other ports right here. Um, check it out, ports, cells. You can check out the port information. Um, you have your layers for your components. Everything's in there for you to kind of play around with and check. You can inspect the simulation once it looks good. Uh, you kind of close out of it, and then it'll go ahead and run your simulation and then display the information at the bottom here. But yeah, so this is super, helpful, for a design flow because it's like, what you need for your project, right? You need a, you know, 1310 MMI or 1550 MMI. You write the MMI in IPCIS, and then you say, okay, MMI is written. Now I need to go ahead and optimize this. You write a, split, or you write a simulation function, um, you know, very simple, right? You're not doing anything crazy here. You're just passing information into functions that already exist. Um, and then you run it, and then you get your transmission and reflection. Then you can take that data and you can, do whatever you need to do with it at that point. Um, there's also, obviously, then you can optimize your component as well. So here is a simple optimization routine that is written inside of IPCIS. So we have an optimize MMI function, takes in all of these parameters. Um, and in the console here, we can see our transmission and reflection that we've gotten from the MMI. And then we have our cost function here that we're using for our optimization. And then we are using SciPy minimize to then do the optimization for our MMI. And then we plot our MMI and return the result. And so this function calls this function, and then yeah, it does the optimization and it prints out the um, final results for you. Then you take that, you go into your IPCIS P cell, and then you go ahead and make a locked property where you fill in all the values for your optimized MMI. And so, like, all of this really just kind of works together to give you like a very straightforward and very like, centralized kind of design flow, right? Like you can do everything at IPCIS. You can make your component, you can make your layout, you can do circuit simulations, time domain simulations. You need to optimize, a component with lumerical. You can very easily, write the simulation for it, write the optimization routine for it, and, do all of that through IPCIS. And I think the one really, kind of important thing as well is that this is all reusable and like reconfigurable. So, like you can, you write the code once and, you can reuse it as many times as you want. You can share it with other people. They can reconfigure it, reuse it as many times as they want. And, it saves time. It saves time. And, yeah, so here's our uh, optimized MMI layout that it generated. And here's the EME simulation. So I do want to stress that the optimization routine didn't use lumerical. It used Cafe, mostly because with lumerical, we'd be sitting here for quite some time. With Cafe, it kind of does it pretty quickly. And now our optimization results are at the bottom here. Um, yeah, so um, yeah, that's all I have for today. I know like we're running out of time, so um, yeah, any questions? All right, if no questions, yeah, if no questions, then thank you again for joining us today. And yeah, if you have any questions, like I guess feel free to email one of us, and we'll get back to you. Thank you,
Okay.
everyone.
Yeah, thank you so much for taking the time to give this workshop.
Yeah, of course. Thank you for having us.
Uh, yeah, thanks. Chloe, I think you can stop the recording now.
Yeah, I will do that.